Somewhere over the Persian Gulf, an Iranian radar operator stares at a screen showing something that shouldn't exist. A contact moving faster than anything in their threat library, crossing their airspace at an altitude where the air is so thin it barely qualifies as atmosphere. They try to hold it. The track slips. They try again, and then it's gone. Out of range. Out of reach. Mission complete on the other end. They never got a lock. This is what happens when you point a missile system at an aircraft that operates outside the physics those systems were built around. Iran's air defense network is one of the most layered in the Middle East, and it still couldn't answer the problem. We're going to break down exactly why, what the SR-72 actually is, how Iran's defenses work, what went wrong during the encounter, and why the result was settled before the aircraft ever crossed the coastline. Most people hear SR-72 and think faster SR-71. That's the wrong mental model entirely. The SR-71 Blackbird was built around the idea of going fast enough that nothing could catch it. Mach 3 plus, high altitude, get in and get out. It worked for decades. But the SR-72 isn't an evolution of that concept. It's a different concept altogether. The thinking behind it is that speed itself becomes a weapon, not just a survival mechanism. There's a gap between those two ideas that matters more than it sounds. Lockheed's Skunk Works, the same team behind the U-2, the SR-71, and the F-117, developed the SR-72 around a propulsion system that doesn't exist anywhere else in operational aviation. It's a combined cycle engine, which means it runs as a conventional turbine at lower speeds and transitions to scramjet propulsion as it accelerates through the hypersonic regime. A scramjet has no moving parts and combusts fuel using air compressed purely by the vehicle's own velocity. Below a certain speed, it produces nothing. But past roughly Mach 4, it takes over and pushes the aircraft toward Mach 6, around 4,500 miles per hour at altitude. That number sounds abstract until you think about what it means for anyone trying to shoot the aircraft down. A surface-to-air missile doesn't fly at your target. It flies at where your target is going to be. The fire control system calculates a point in space. The missile heads for that point, and if the prediction is accurate, you get an intercept. That calculation depends on having enough time to run the math and enough track data to make the prediction reliable. At Mach 6, the SR-72 crosses a typical radar engagement zone in seconds. The fire control system has almost no data to work with, the prediction window collapses, and the intercept solution never solidifies. Speed at this level also works against detection in ways that aren't obvious. The aircraft runs hot. Hypersonic friction heats the airframe to extreme temperatures. But it also operates at altitudes near the top of the stratosphere, where most ground-based radar systems aren't optimized to look. The geometry of radar coverage has a ceiling, and the SR-72 operates close to it. That means the radar picture is already degraded before you factor in any low observable design features the aircraft carries. Now, the fair question the audience always asks, is the SR-72 actually operational, or is this still a program? The honest answer is that it lives in a gray zone. Lockheed has confirmed the program exists. The U.S. Air Force has referenced hypersonic reconnaissance capabilities without naming the platform. Operational deployment details are classified. That ambiguity isn't accidental. The uncertainty about where the aircraft is and what it can do is itself part of the deterrent. An adversary who doesn't know whether you're overhead right now has to behave as if you might be. Every air defense system flying today was designed before hypersonic cruise platforms became real. The SR-72 is the first aircraft that makes those systems structurally obsolete. So that's the machine. Now you need to understand what it was flying into. Iran didn't build its air defense network overnight, and it didn't build it cheap. What exists today is one of the most layered systems in the Middle East, assembled over decades from a mix of Russian hardware, domestically engineered platforms, and a command structure that ties them together across the country's most sensitive airspace, including the Gulf. The centerpiece of the Russian-supplied portion is the S-300. This isn't a simple radar-guided missile battery. The S-300 was engineered specifically to engage fast, high-altitude threats. Ballistic missiles, fast jets, low observable aircraft, It operates across multiple frequency bands, can track dozens of targets simultaneously, and was built with the assumption that any serious adversary would try to jam or spoof its guidance. Iran received its first operational S-300 systems in 2016 after a lengthy embargo and has spent years integrating them into a unified command network with overlapping coverage zones. On paper, it's a serious capability. Then there's the Bavar 373. Iran developed this platform domestically, positioning it as their answer to the US Patriot system. Iranian military officials have claimed it can engage stealth aircraft and fast-moving cruise missiles. Independent verification of those claims is essentially impossible, but the engineering effort behind it is real, and the system has gone through multiple public test cycles. Whether it performs at its claimed ceiling in a contested environment against a real hypersonic target is a different question entirely. Beyond the missiles themselves, Iran runs an early warning radar network covering the Gulf approaches. Radar stations positioned across the southwestern coast and on islands in the Gulf give operators significant coverage of the maritime approaches, the same routes U.S. reconnaissance assets use regularly. Iranian operators have tracked American drones, monitored Israeli aircraft transiting the region, and logged cruise missile trajectories from multiple conflicts in the area. This is not a green crew running unfamiliar equipment. The people watching those screens have real operational experience. So why wasn't any of it enough? Air defense doesn't fail at one point, it fails across a chain. Detection, tracking, lock-on, and intercept are 4 separate steps, and every single one has to succeed for a missile to leave the rail with a valid solution. Miss any step or run out of time between them, and the sequence collapses. The S-300 and the Bavar 373 were both designed with threat models in mind. Specific speed ranges, altitude bands, and radar return profiles that their engineers used to tune the systems. Those threat models reflected real adversaries at the time of design. Mach 6 wasn't in the calculation, because nothing flying at Mach 6 existed when these systems were being built. That's not a criticism of Iranian engineers. It's a problem every air defense program in the world shares. Now put that system up against the SR-72, and here's where the encounter gets interesting. By 2026, the Persian Gulf region had been running hot for months. Strikes, counterstrikes, maritime incidents, and proxy activity across multiple fronts had pushed U.S. reconnaissance operations into a higher tempo. Knowing what's happening inside Iran's military infrastructure, where assets are moving, what's being activated, what's being concealed, carries enormous operational value when you're managing that kind of environment. The SR-72 went in to get that picture. Iranian early warning radar picked up the contact somewhere over the Gulf. What the operators saw didn't match anything in their reference library. The return was intermittent, appearing, dropping out, reappearing, and the velocity reading was beyond the scale of conventional fast movers they'd seen before. Not a cruise missile, which would track predictably and slowly enough to solve. Not a conventional aircraft. Something else, moving through their coverage zone at a speed that gave the system almost no time to build a track. Here's what that looks like from the operator's side. When a radar contact appears, the fire control system starts building a track, logging successive positions to calculate heading, speed, and predicted future location. That prediction is what guides the missile. The more track data you have, the more accurate the prediction. Against a Mach 6 target crossing a radar engagement zone, you might get 1 or 2 position updates before the aircraft is already past the point where any intercept geometry is viable. The fire control computer needs time to solve the problem. At that speed, time is the one thing the system doesn't have. Iranian operators attempted to establish a fire control lock. The radar couldn't hold the track consistently enough to hand off a valid firing solution to the missile system. The contact was intermittent because the SR-72's radar cross-section is reduced, not invisible, but small enough that a high-speed target with a weak return becomes extremely difficult to track continuously. Stack that on top of the altitude factor, which puts the aircraft near or above the optimal engagement ceiling for ground-based systems, and the intercept problem goes from difficult to geometrically unsolvable. No missile left the rail, not because someone made a political decision to stand down, but because the conditions for a valid shot never materialized. The SR-72 completed its reconnaissance run, collected what it came for, and exited the area. What remained in Iranian radar logs was a contact that had appeared, refused to cooperate with any of the systems pointed at it, and disappeared before anyone could do anything about it. That's what happened. Here's why it was always going to go that way. The SR-71 flew operational missions for more than 2 decades without a single aircraft lost to enemy fire. Not once. Adversaries launched missiles at it. North Korea, North Vietnam, Libya, and none of them connected. The reason wasn't that those missiles lacked the range or the altitude. Some of them did have both. The reason was that by the time a launch was authorized, the Blackbird had already moved far enough that the intercept geometry had fallen apart. Human decision-making takes time. Radar operators have to confirm the contact. A commander has to authorize weapons release. The missile has to be brought to readiness. That chain, even when it runs fast, takes longer than a Mach 3+ aircraft needs to exit the danger zone. The SR-72 runs at twice that speed. The decision chain doesn't get faster just because the target does. So what was already a narrow window for the SR-71 becomes, against the SR-72, essentially theoretical. You'd need to predict where the aircraft is going to be, authorize a shot, and launch, all before the target has moved so far that your solution is worthless. In practice, that sequence can't complete in time against a Mach 6 platform with a reduced radar return at high altitude. This is what the phrase "speed as a weapon" actually describes. It's not about surviving a missile that gets launched at you. It's about making sure the launch never happens, because the conditions for a valid shot never exist long enough for anyone to pull the trigger. The threat neutralizes itself through physics before it ever becomes a real danger. The geopolitical dimension of that is deliberate. When the US can send a reconnaissance platform into contested airspace, collect what it needs, and exit before any adversary finishes the engagement sequence, it changes the calculation for every country operating air defenses in the region. You can't deter something you can't stop, and you can't negotiate around a capability gap you don't know how to close. Iran's air defense operators did what they were trained to do. The equipment responded the way it was designed to respond. The failure wasn't human, it was structural, built into every assumption those systems were engineered around, years before the SR-72 existed. Speed at hypersonic levels doesn't just beat interceptors, it beats the people operating them, because humans can't compress their decision cycle fast enough to matter. Iran's attempt to lock on wasn't reckless, it was just physics working against them in every direction at once. No upgrade to the S-300 or the Bavar 373 closes that gap without solving a problem that no air defense program in the world has answered yet. The US Air Force has tried to retire the Warthog for years, but it is still flying combat missions today. Built in the 1970s, the Fairchild Republic A-10 Thunderbolt II is still flying combat missions in one of the most dangerous regions in the world, tracking fast-moving threats in the Strait of Hormuz. So how does a 50-year-old warplane stay relevant in the age of stealth jets and hypersonic weapons? And what is it doing today that modern fighters still can't replicate? Join us as we reveal why the Warthog refuses to disappear and how Iran is currently paying the price for that. Let us start with the sound, one of the things the Warthog is famous for. When an A-10 fires its cannon, the noise it makes sounds like the sky is tearing open. A deep, violent, mechanical roar that lasts less than 2 seconds but feels like it goes on forever. Pilots who have heard it from the cockpit describe it as unlike anything else in aviation. Ground troops who have heard it from below describe something closer to relief, the particular kind of relief that comes from knowing that whatever was about to harm you is no longer a threat. That sound is the GAU-8 Avenger, a 30mm rotary cannon that is not just a weapon mounted on an aircraft. It is the reason the aircraft exists in the first place. The A-10's entire airframe was designed around the GAU-8. The aircraft was built to carry that gun into battle, and every other design decision, the engines, the wings, the cockpit, and the landing gear were made in service of that central function. The GAU-8 fires at a rate of 3,900 rounds per minute. Its average recoil force is 10,000 pounds, which is slightly more than the thrust output of each of the A-10's two engines. The rounds it fires are accurate enough to put 80% of shots within a 40-foot diameter circle from 4,000 feet while the aircraft is in flight. In a world that increasingly debates whether human pilots are even necessary, where the conversation is dominated by stealth, hypersonics, and artificial intelligence, the A-10 is the most stubbornly analog weapon in the American arsenal. It flies low and slow. It gets close to things and shoots them with a cannon until they stop being a threat. That is not a philosophy that fits neatly into a PowerPoint about sixth-generation air dominance. But it turns out that philosophy is devastatingly effective in the specific conditions where Iran decided to pick a fight. To understand why the Warthog is in the Middle East right now, let's go back to the beginning and understand what this aircraft was actually built to do. The A-10 was born from a very specific fear. In the 1960s and 70s, American military planners looked at the Soviet Union's massive tank force and asked a deeply uncomfortable question. If the Red Army rolls into Western Europe, what stops it? The answer they arrived at was an aircraft designed from scratch to destroy armored vehicles as quickly and as cheaply as possible, in the most dangerous conditions imaginable, and then come home. The result was an aircraft with a titanium-armored cockpit nicknamed the Bathtub, redundant flight systems designed so the aircraft could continue flying after taking significant damage, and an airframe robust enough to return to base with one engine destroyed, one tail damaged, or significant wing damage. The Warthog was built to survive being hit and keep fighting anyway. During Desert Storm alone, A-10s destroyed over 900 Iraqi tanks, around 2,000 military vehicles, and nearly 1,200 artillery systems. It even reportedly shot down 2 Iraqi helicopters, a rare feat for a ground attack aircraft that carries no radar and was never intended for air-to-air combat. After Desert Storm came Kosovo, then Afghanistan, then Iraq again, then Libya, then Syria. Every time the military establishment declared the Warthog obsolete, another conflict arose in which it proved to be exactly the right tool for exactly the right job. The Air Force, for its part, has been trying to retire the A-10 for years. The argument is straightforward and not without merit. The aircraft is slow and non-stealthy, built for low-altitude attacks that become genuinely dangerous against modern air defenses, equipped with man-portable missiles and radar-guided guns. Advanced air defense systems from Russia and China can engage it long before it reaches its target. The Air Force argues that modern multi-role fighters equipped with precision-guided munitions can perform close air support from safer altitudes, and that the money spent maintaining an aging fleet of specialized aircraft would be better directed toward next-generation capabilities. The Air Force's fiscal year 2026 budget included a request for $57 million to retire all 162 remaining A-10s, 2 years ahead of schedule. The plan was clear. The Warthog was done. However, the Congress disagreed again. The fiscal year 2026 National Defense Authorization Act prohibited the Air Force from reducing the A-10 inventory below 103 aircraft and required at least 93 primary mission aircraft through September 30th, 2026. Any further reduction required a unit-by-unit waiver process, a 30-day notification period, and a multi-year transition plan covering 2027 through 2029, mandated by March 31st, 2026. Congress essentially looked at the Air Force's retirement plan and said no. Keep the Warthog flying. And then, less than 3 months later, Operation Epic Fury began, and the aircraft that was supposed to be in the process of being retired found itself in the opening wave of the largest American military campaign in the Middle East in over 2 decades. U.S. Central Command confirmed that a 10 Thunderbolt II aircraft were employed during the first 48 hours of Operation Epic Fury against Iranian targets, integrated into the initial strike wave from the very beginning of the campaign, not called in as backup, not deployed as an afterthought, in the opening salvos. The first official images CENTCOM released of the A-10 in action during Epic Fury told a story about the variety of threats it was being sent to handle. The aircraft were carrying a mixed loadout: AGM-65 Maverick air-to-surface guided missiles, LAU-131 rocket pods loaded with laser-guided rockets, AIM-9 Sidewinder air-to-air missiles for self-defense, a Lightning targeting pod for precision identification of targets, and a 600-gallon external fuel tank for extended loiter time. That loadout tells you something important about the threat environment in Epic Fury. The Maverick missiles are for armored targets and hardened positions. The laser-guided rockets are versatile precision weapons that can engage small, fast-moving threats at relatively low cost. The Sidewinders suggest the possibility of engaging Iranian drones in the air, which have become a significant threat across the region. And the 600-gallon fuel tank says that whoever loaded this aircraft expected it to stay airborne over the target area for a long time, ready to respond to whatever emerged. CENTCOM emphasized precisely this capability in the statement accompanying the A-10 imagery. The aircraft can remain on station for hours, standing ready to execute a mission whenever needed. That word, loiter, is the one that appears again and again in every discussion of why the A-10 remains relevant. Multi-role fighters can deliver more sophisticated weapons from greater distances, but they cannot circle over a target area for hours at a time, watching for threats to emerge, waiting for a boat to appear around a headland or a missile launch team to move positions. The A-10 can, and in the geography of the Strait of Hormuz, that capability proved decisive. Chairman of the Joint Chiefs of Staff General Dan Kane confirmed at a Pentagon press conference that the A-10 Warthog is now engaged across the southern flank of Operation Epic Fury, hunting and killing fast-attack watercraft in the Strait of Hormuz. The Strait of Hormuz is one of the most strategically important bodies of water on Earth. Roughly 20% of the world's daily oil supply transits the strait. Iran has long maintained a strategy of threatening to close the strait to shipping in any serious conflict, using swarms of fast attack boats, mines, and coastal missiles to make passage too dangerous for commercial vessels. It is an asymmetric threat that does not require Iran to defeat the U.S. Navy in a conventional sense. It just needs to make insurance companies decide that sending tankers through the strait is too risky. The economic disruption that follows can be devastating for regional states, for global energy markets, and for any American effort to sustain regional alliances. Iran's fast attack boat strategy is built on numbers and speed. Small, fast vessels, difficult to track, appearing from coastal inlets and islands, capable of laying mines or firing missiles before air defense systems can respond effectively. Against an F-35 operating at altitude, these boats are genuinely hard to engage. They are fast, small, low on the water, and easy to lose against the radar clutter of a busy coastline. Against an A-10 flying low and slow at 300 knots with a targeting pod, a Maverick missile, and a pilot who has been training for exactly this scenario for years, they are not hard to find at all. The A-10 was specifically trained for the maritime role of hunting Iran's fast boat fleets long before Operation Epic Fury began. In early February 2026, A-10s were conducting close air support missions for the USS Santa Barbara in the Arabian Gulf as part of the force buildup ahead of the campaign, protecting mine-hunting operations in constrained waters near the strait from fast boat swarms and mining threats. In a March 16th video, CENTCOM Commander Admiral Brad Cooper stated that U.S. forces had destroyed more than 100 Iranian naval vessels and vowed to continue rapidly depleting Iran's ability to threaten freedom of navigation in and around the Strait of Hormuz. 100 vessels. And the A-10 was actively contributing to that tally, not as a supplementary platform, but as one of the primary tools the U.S. military chose to clear the strait. A-10s were also spotted with Sidewinder missiles engaging Shahed-type Iranian drones during counter-unmanned aerial systems missions, an air-to-air role that nobody designed the Warthog for, but which pilots have adapted to over years of operational deployment in environments flooded with cheap Iranian drones. As the campaign expanded, flight tracking data revealed that the Air Force was preparing to send additional A-10s across the Atlantic toward the Middle East, with 12 aircraft arriving at RAF Lakenheath in late March 2026, suggesting a significant expansion of the Warthog's role in the campaign. The aircraft that the Air Force was actively trying to retire 6 months earlier was being reinforced mid-conflict. The debate about the A-10's future will continue after Epic Fury ends, but right now, somewhere over the Strait of Hormuz, an aircraft designed in the 70s to kill Soviet tanks, is flying low over contested waters, scanning for Iranian fast boats, and making the Islamic Revolutionary Guard Corps pay for the mistake of thinking that cheap, swarming naval tactics could close the world's most important oil choke point without consequence. The upgraded F-22 Raptor is challenging global defense norms. With enhanced stealth, improved engines, and advanced sensor fusion, its air superiority is redefined. Critics warn these changes could trigger an arms race, while others argue it secures U.S. dominance. Meanwhile, China and Russia are investing in next-generation fighter technologies to lead the innovation race. As Beijing and Moscow ramp up their modernization efforts, the critical question remains: can the F-22 maintain its supremacy, or will emerging platforms like the F-47 usher in a new era of aerial warfare? Join us as we uncover the cutting-edge upgrades of the F-22 Raptor, advancements so powerful they've captured China's attention. The F-22 Raptor is one of the most advanced fighter jets ever built, but it didn't start out that way. It began as part of the U.S. Air Force's Advanced Tactical Fighter program in 1981. The goal was to replace the F-15 and F-16, which were powerful but becoming vulnerable to new Soviet threats. The Soviets were developing advanced missiles, airborne warning systems, and new fighters like the Su-27 and MiG-29, which could challenge U.S. air superiority. To stay ahead, the U.S. needed a fighter that was faster, stealthier, and more advanced. Engineers designed the ATF to dominate in a future war, using cutting-edge technology like lightweight materials, better flight controls, and engines that allowed supercruise. Sustained supersonic flight without using fuel-hungry afterburners. Most importantly, it had stealth capabilities, making it nearly invisible to enemy radar. After years of competition, Lockheed YF-22 won against Northrop's YF-23 in 1991. While the YF-23 was stealthier and faster, the YF-22 was more maneuverable thanks to its thrust-vectoring engines, which allowed it to perform sharp turns and outmaneuver enemies in close combat. Lockheed's design also had fewer risks, making it the Air Force's top choice. Over the years, the F-22 has received multiple upgrades to keep it at the top of the game. Originally built for air-to-air combat, it has been enhanced to handle air-to-ground missions with precision bombs, making it more versatile. Its avionics have been upgraded, including better radar and sensor fusion, allowing pilots to detect and track threats even more effectively. One of the biggest improvements is its stealth maintenance. When the F-22 first entered service, its stealth coatings required a lot of upkeep, but new materials have made it more durable and easier to maintain. This means less downtime and more time in the air, ready for action. The F-22's weapon systems have also been enhanced. It now uses improved AIM-9X Sidewinder missiles for short-range dogfights and AIM-120D AMRAAM missiles for long-range engagements. Additionally, new software upgrades have given it the ability to communicate better with other aircraft, improving its role in networked warfare. While the Air Force stopped producing the F-22 after building 186 jets, it has continued to receive technological upgrades. Some of these improvements come from lessons learned during the development of the upcoming next-generation air dominance fighter, and they have enhanced the fighter jet's ability to detect, track, and eliminate threats before they even know it's there. These technological upgrades have significantly strengthened one of the F-22's most critical advantages: its radar and sensor systems. The jet's AN/APG-77 radar allows pilots to spot enemy aircraft from extreme distances while staying undetected. This radar uses active electronically scanned array technology, which improves tracking and targeting while reducing the chance of being detected by enemy systems. Combined with powerful jamming capabilities, the F-22 can disrupt enemy communications and radar, making it even harder to counter. The F-22 doesn't just rely on stealth, it's also armed with some of the deadliest air-to-air weapons in the world. The AIM-120 AMRAAM missile is its primary long-range weapon, designed to engage enemy aircraft before they get close. For close-range combat, the AIM-9X Sidewinder offers unmatched agility, allowing the Raptor to take down threats even during high-speed dogfights. Additionally, the F-22 carries an M61 Vulcan 20mm cannon, a 6-barrel rotary gun capable of firing 6,000 rounds per minute. This provides a powerful backup for situations where missiles aren't an option. Speed and agility are key to the F-22's dominance. Its thrust vectoring nozzles give it unmatched control in the air, allowing it to perform maneuvers no other fighter can match. Whether it's executing high G turns, rapid climbs, or sudden dives, the Raptor can outmaneuver opponents with ease. This ability is critical in dogfights, where the slightest advantage can mean the difference between victory and defeat. Former pilots often describe flying the F-22 as effortless, with its advanced flight controls making complex maneuvers feel smooth and precise. This agility ensures the Raptor can engage and disengage at will, giving its pilots complete control over the battlefield. While the F-22 is already a technological marvel, ongoing software and hardware upgrades will keep it ahead of emerging threats. The F-3R, that is, Form, Fit, Function, Refresh program, is enhancing the aircraft's avionics, increasing its processing power and sensor capabilities. These improvements will make the Raptor even deadlier, allowing it to integrate with next-generation systems and unmanned drones in future combat scenarios. The Air Force is also working on engine enhancements to boost efficiency and power, ensuring the Raptor remains capable of supersonic speeds without afterburners. These updates will extend the F-22's operational life, keeping it in service for years to come. Last year, Lockheed Martin successfully ran 6 flight tests to add new high-tech features to the stealth fighter. The U.S. Air Force relies heavily on its fleet of F-22s, and these upgrades will help keep the jet at the top of its game, possibly all the way into the 2040s. Some of the biggest improvements include a new infrared defensive system, advanced sensors, and special stealthy drop tanks that extend its range. At the 2025 Air and Space Forces Warfare Symposium, Lockheed Martin shared updates about these developments. Right now, the Air Force has about 180 F-22s, though 32 of them are older models used only for training and testing. Mike Shoemaker, a top executive at Lockheed Martin, emphasized the significance of the upgrades, stating that modern fighter jets must have enhanced vision, quicker threat detection, and extended strike capabilities. He mentioned that recent flight tests had concentrated on integrating advanced sensors to improve the F-22 Raptor's ability to track and engage targets from much greater distances, significantly boosting its combat advantage. While Lockheed Martin didn't share specific details about these sensors, the Air Force has been testing stealthy underwing pods on the F-22 for years. Many experts believe these pods house an advanced infrared search and track system, which would allow the Raptor to detect enemy aircraft without using radar, perfect for staying hidden while hunting down threats. Another major improvement coming to the F-22 is its next-generation infrared defensive system. Mike confirmed that Lockheed Martin is already under contract to integrate this technology, which will give the Raptor better missile warning capabilities and long-range detection. In simple terms, this means the jet will not only be better at spotting enemies, but also at avoiding surprise attacks. Lockheed Martin previously revealed that IRDS will use a distributed sensor system based on Hyperspeed technology, first introduced in 2022. Hyperspeed sensors provide a constant infrared view of the battlefield, helping pilots detect and track threats, even in complete darkness. So far, these sensors have only been fully integrated into F-5 advanced Tiger jets used by private military contractors. Now they're making their way to the world's most advanced stealth fighter. Mike's comments confirm that the F-22's new advanced sensor upgrade is different from the infrared search and track distributed system. This suggests that the Raptor may get even more advanced infrared tracking capabilities. Adding an extra infrared sensor pod alongside IRDS makes sense. Traditional IRST systems, whether built into jets or carried as external pods, typically use large, swiveling sensors to track targets from different angles. TAC IRST, the system being developed for the F-22, works differently. In 2017, Ken Merchant, a Lockheed Martin executive for the F-22 program, explained that there wasn't enough space inside the jet to install a full IRST system like the F-35's Electro-Optical Targeting System, or EOTS. EOTS mainly helps with air-to-ground targeting, but it also has infrared tracking capabilities. Even on its own, IRDS would be a huge improvement over the F-22's current ANAAR-56 missile launch detector, which only provides basic infrared warnings. TASI IRST sensors spread across the aircraft could help the Raptor detect threats more effectively, similar to how the F-35 distributed aperture system works. Using both built-in and podded IRST sensors together would be a game changer. As experts have explained, traditional IRST sensors can only detect a target's direction and movement, but struggle to determine its exact range. However, if two aircraft with IRST systems share data, they can quickly triangulate a target's position with precision. Lockheed Martin has already demonstrated this kind of teamwork using its Legion pod, which features an IRST-21 sensor. This system can provide high-quality targeting data and has been tested on various fighter jets. The F-22 was originally supposed to have an IRST system, but budget cuts removed it late in development. Now, with stealth technology becoming more common worldwide, the U.S. military sees infrared tracking as crucial. Unlike radar, which actively sends out signals that enemies can detect, IRST works passively. It simply listens for heat signatures, making it perfect for tracking stealth aircraft. IRST can also help radar systems lock onto targets more effectively, providing better accuracy without revealing the jet's position. One of the biggest advantages of IRST is that it's immune to electronic warfare. Modern enemy forces use jamming technology to disrupt radars, but infrared tracking can't be blocked in the same way. This makes IRST a powerful tool for detecting and tracking stealthy threats. Mike reassured that any new F-22 upgrades would maintain the aircraft's stealth capabilities. This is crucial as the U.S. faces increasing threats from advanced enemy aircraft and stealthy weapons. China, for example, recently unveiled two new stealth fighter designs, signaling rapid advancements in their air combat technology. He also emphasized the importance of detecting threats from greater distances in modern air combat. He explained that if an aircraft could sense and see farther, it would also be able to share that information with other units. The F-22 Raptor had already proven itself as one of the most advanced fighters, acting as a central coordinator for larger aerial teams. Mike noted that it could gather intelligence, guide other aircraft, and ensure air superiority. Lockheed Martin, alongside the U.S. Air Force and industry partners, had been working to enhance the Raptor's communication and networking abilities to further improve its role in battle. According to Lockheed Martin, the F-22 was the first combat aircraft to fully utilize an open mission systems architecture, which allowed for faster and easier software upgrades. This feature made the aircraft highly adaptable to new technologies. A major software update known as Release 4 was in its final testing phase. If everything proceeded as planned, the update would be available for the entire F-22 fleet by the end of the spring. He also pointed out that this upgrade would make it easier to integrate third-party applications into the aircraft's mission systems, enhancing its capabilities even further. When discussing the timeline for the Raptor's new sensor capabilities, Mike mentioned that they were expected to be delivered to the fleet within the next few years. In the meantime, he highlighted that the F-22 remained in high demand. It was also revealed that Lockheed Martin had been supporting increased operations and deployments despite the relatively small size of the F-22 fleet. He acknowledged the challenges of maintaining a fleet that had accumulated over 500,000 flying hours, but reassured that the aircraft would not require major structural upgrades to continue serving well into the 2040s. The long-term future of the F-22, however, remained tied to the Air Force's next-generation air dominance program. Originally designed to replace the Raptor, NGAD had undergone a detailed review the previous year. It was suggested that the analysis appeared to favor continuing the program as planned, although concerns about affordability persisted. Developing a next-generation fighter required significant funding, which had to be balanced with other military priorities, such as stealth refueling tankers and AI-powered drone wingmen, known as collaborative combat aircraft. Additionally, rising costs in the Sentinel intercontinental ballistic missile program had forced the Air Force to reassess its budget. Shoemaker also mentioned that discussions were still ongoing regarding the optimal size of the B-21 Raider stealth bomber fleet. Meanwhile, the Department of Defense was facing potential budget cuts to existing programs in order to redirect resources toward new priorities, including the Golden Dome missile defense system. Despite these uncertainties, Lockheed Martin remained confident in the F-22's continued importance. It was indicated that the aircraft's upgrades were already contributing to NGAD research, ensuring its relevance in modern air combat. However, as the U.S. Air Force moves forward with the next generation of fighters, a major shift is underway. The recent unveiling of the F-47, the Air Force's newest jet, marks a significant leap beyond the F-22, offering superior range, stealth, and cost-effectiveness. Air Force Chief of Staff General David W. Alvin, who spoke at a high-profile event alongside former President Donald Trump, revealed new details about this once-secret aircraft. Alvin reportedly stated that, despite claims from adversaries, the F-47 would be the first crewed sixth-generation fighter in the world. His comments were seen as a response to China, which had recently unveiled its own stealth aircraft. He explained that the F-47 would join the B-21 Raider stealth bomber in the Air Force's new fleet and would be equipped with advanced stealth technology, next-generation sensors, and long-range attack capabilities. These features, he noted, would make the aircraft highly effective in contested battle zones. Although the Air Force did not reveal all details about the F-47, the concept images released showed notable design differences compared to previous fifth-generation fighters like the F-22 and F-35. Observers noted that while the F-47 had a traditional, stealthy nose and bubble canopy, it also included forward canards and sharply angled wings, features not commonly associated with stealth aircraft. Alvin reportedly emphasized that the F-47 would have a significantly longer range than the F-22. The existing F-22 could fly more than 1,850 miles with external fuel tanks before needing to refuel, but the F-47 was expected to exceed that distance considerably. Discussions within the Air Force had suggested the possibility of producing two variants of the aircraft, one larger version designed for long-range missions, particularly in the Pacific, and another smaller version optimized for shorter-range operations in Europe. According to the Air Force, the F-47 represents a major leap forward and had been designed with a modular system that would allow it to be upgraded over time. Officials expressed confidence that this approach would ensure the aircraft remained effective for decades. Alvin further explained that for the past 5 years, the Air Force had been testing NGAD technologies using experimental X-planes. These test aircraft had flown hundreds of hours, helping engineers refine advanced systems and accelerate the development process. He stated that this extensive testing had allowed them to push the limits of technology and bring the fighter into service more quickly than previous programs. He also reportedly expressed confidence that the F-47 would be operational within former President Trump's administration, which would last until January 2029. Comparisons were made to the F-22, which took 6 years to progress from selection in 1991 to its first production flight. It was also noted that references to NGAD test flights had surfaced as early as 2020. However, former Air Force Secretary Frank Kendall had later revealed that prototype flights had likely taken place even earlier, possibly in the mid-2010s. One of the biggest issues with the F-22 was its cost. While the basic construction of each jet cost around $140 million, once research, development, and other expenses were included, the price soared to about $350 million per aircraft. Now, with the Next Generation Air Dominance program, the Air Force plans to field between 220 and 250 advanced fighters. The F-47, a product of this effort, is expected to be a game-changer. Unlike older stealth aircraft, which required extensive maintenance to keep their radar-evading surfaces intact, the F-47 will feature a more durable design, reducing downtime and making it combat-ready more often. This design philosophy follows lessons learned from the new B-21 Raider bomber, which was built to fly frequently without excessive maintenance. The F-47 is also built for adaptability. Thanks to digital engineering and an open systems approach, its software, sensors, and mission equipment can be upgraded quickly and easily. It will also need fewer crew members and ground support to operate, making it more flexible in real-world missions. Boeing won the contract to develop the F-47, which will now enter its engineering and testing phase. Initially, a small number of test aircraft will be produced, with options for further production later. Boeing stated that this fighter will continue its legacy of building some of the most famous aircraft in U.S. history, including the P-51 Mustang, F-15 Eagle, and F/A-18 Hornet. The decision to select Boeing over Lockheed Martin was surprising to some. Boeing has faced issues with several military projects, such as the KC-46 tanker and T-7 trainer, resulting in significant cost overruns. Meanwhile, Lockheed, the maker of the F-22 and F-35, has struggled with delays in upgrading the F-35's technology and managing its high maintenance costs. However, the Air Force has not publicly shared the reasons behind its choice. Despite the debates surrounding the selection process, the Air Force remains focused on ensuring air superiority. The next-generation fighter is expected to dominate the skies, keeping the U.S. ahead of threats for decades. Meanwhile, the F-22 will remain a key part of the USF's fleet, benefiting from upgrades until its eventual replacement by the Boeing F-47, ensuring continued air superiority well into the future. Dozens of contacts, all moving fast, all closing on the same point. That's what the radar picture looks like when an Iranian drone swarm is inbound. Not one threat, not two, but a wall of cheap flying machines coming from multiple directions at once, each one designed to make sure the ship in front of them runs out of ways to fight back. 5 years ago, that was a real problem with no clean answer. Today it isn't, because somewhere in that engagement, a beam of focused light starts working through the swarm one drone at a time, and the drones just stop flying. No warning, no explosion at range. They just fall. Iran built its entire naval harassment strategy around a vulnerability that no longer exists. And that's the story we're getting into right now. Why Iran built a drone swarm strategy in the first place. To understand why this matters, you have to start with Iran's actual military situation, because Iran didn't build a drone swarm strategy because it wanted to. It built one because it had no other choice. Iran can't fight the U.S. Navy head-to-head. That's not an opinion, it's just arithmetic. A U.S. carrier strike group carries more air power than most countries' entire air forces. Iran's surface fleet is aging, its air force runs on decades-old American hardware, it can no longer get parts for, and its Navy doesn't have the blue water capability to project force beyond the Gulf. Conventional confrontation with the U.S. would end badly and quickly, so Iran went a different direction. Instead of trying to match American capability dollar for dollar, they built a strategy around volume and cost. Send enough cheap things at a problem, and eventually the problem runs out of expensive solutions. The Shahed series drones are the heart of that approach. They're not sophisticated. They fly slow, they're relatively easy to detect on radar, and they don't have the kind of electronics you'd find on a military aircraft. What they have is price. A Shahed 136 costs somewhere in the range of $20,000 to $50,000 to produce. A standard missile intercept costs over $2 million. Send 20 drones at a ship and force it to fire 20 missiles, and you've just burned through $40 million worth of the enemy's inventory for under $1 million of your own. That's a trade Iran wins every time. And the strategy had real teeth. In 2019, drone and cruise missile strikes hit the Saudi Aramco processing facilities at Abqaiq and Khurais, knocking out roughly 5% of global oil supply overnight. The attack, in which U.S. officials linked to Iranian hardware, showed the world that this wasn't theory. Cheap aerial munitions could reach high-value targets and cause serious damage before anyone could stop them. In the Red Sea, Houthi forces backed by Iranian weapons and training ran the same playbook against commercial shipping and U.S. Navy warships for months. The USS Carney alone fired over 100 interceptor missiles in a single deployment period, defending against drone and missile attacks. 100 missiles. Gone. At sea, you can't just reload. A ship carries what it carries, and once the magazine runs low, the options get thin fast. That's the vulnerability Iran was targeting. Not the armor, not the sensors, not the crew, the inventory. Western navies are built around expensive precision weapons that you can only carry so many of, and Iran was betting it could keep sending cheap drones until those weapons ran out. For a while, the bet looked reasonable. Then the U.S. Navy started putting a very different kind of weapon on its ships. What the U.S. Navy's laser weapons actually are. The system the U.S. Navy has been quietly putting on its surface ships is called Helios. high-energy laser with integrated optical dazzler and surveillance. USS Preble was the first destroyer to receive it, making her the first operational U.S. surface combatant to carry a solid-state laser weapon. Not a prototype sitting in a lab, not a test rig on a barge, a combat-ready system mounted on a warship operating in real threat environments. The physics behind it are simpler than you might expect. Helios focuses a high-powered beam of light onto a target and holds it there. The energy transfers into the surface material as heat, and it keeps building until something fails. The airframe warps, the engine seizes, the fuel ignites, or the electronics fry. There's no warhead, no shrapnel, no projectile traveling downrange. Just a sustained column of thermal energy moving at the speed of light, delivered precisely where the fire control system points it. What that means in practical terms is a cost per shot figure that sounds made up until you look at how the system actually works. Each firing costs roughly $1 in electricity. That's it. Compare that to the missile intercept costs we already covered, and you start to see why the Pentagon kept pushing this program even when early versions underperformed. The magazine situation is what really separates this from every other weapon on the ship. As long as the ship's power generators are running, the laser can keep firing. There's no reload, no resupply run, no hard limit on engagements per sortie. In a prolonged drone harassment campaign, exactly the kind Iran has been running in the Gulf, that's not a minor advantage. It's a structural one. Helios also isn't a single-mode weapon. At lower power settings, the dazzler function can blind the optical sensors on a surveillance drone without destroying it. Useful when the rules of engagement require a measured response. Step up the power and you can disable propulsion systems or cook the electronics without the airframe coming apart. Go to full power and you're burning through the drone itself. The operator picks the effect, the system delivers it. Before Helios, the Navy was already fielding a lower power version called Odin, Optical Dazzling Interdictor, Navy. Odin went on multiple surface ships first, which gave the service real operational data on how directed energy performs outside a test range. Humidity, sea spray, atmospheric turbulence, all of it affects how a laser beam holds together over distance, and you can't simulate that in a lab. Odin gave the Navy years of that data before Helios ever went to sea. The limitations are real and worth stating plainly. Heavy rain or thick fog degrades beam quality significantly because the atmosphere scatters the energy before it reaches the target. The system also needs to hold its beam on a target for several seconds to achieve a kill, which means a target that's maneuvering hard at long range is harder to engage reliably. Against a supersonic anti-ship missile pulling high G turns, a laser at current power levels isn't your first line of defense. But slow, straight-flying drones on a fixed approach path? The dwell requirement barely matters. A Shahed flying a pre-programmed route at low altitude isn't doing anything to break the beam's lock. It's just flying in a straight line toward a ship that's now pointing something at it that doesn't miss and doesn't run out of ammunition. The encounter, laser versus drone swarm. Picture the scenario the U.S. Navy has been wargaming for years. A destroyer operating in the Persian Gulf, well inside the range corridor Iran uses for its drone operations. The radar picture fills with contacts. Not one or two, but a coordinated wave coming in from multiple bearings at once. Some are high, some are skimming low over the water to complicate the tracking picture. This is the swarm profile Iran has rehearsed, and it's specifically designed to split a ship's defensive attention across too many targets simultaneously. Against a traditional layered defense, this is where things get ugly fast. The Phalanx close-in weapon system can engage incoming threats, but it covers a limited arc, burns through its 20mm ammunition quickly, and by the time drones are close enough for Phalanx to reliably engage them, you're already in a bad position. Standard missiles are accurate, but as we covered, there aren't unlimited rounds on board, and they're wasted on a $20,000 drone. Electronic jamming works against drones that rely on GPS or radio command links, but Shahed-type systems fly pre-programmed routes, cut the signal, and they just keep going. None of the traditional answers solve the volume problem cleanly. Helios approaches the same problem differently. The fire control system pulls track data from the ship's radar, assigns priority to the targets posing the most immediate threat, and the beam slews onto the first contact. Slew, dwell, kill, move. The mechanical turret repositions fast enough that the transition between targets takes a fraction of a second. There's no reload cycle between engagements, no cooldown that a swarm operator could try to exploit. The system works through the contacts sequentially, and the engagement rate is measured in seconds per drone, not minutes. The actual kill mechanism depends on where the beam holds. On a drone with a combustion engine, sustained heat on the fuel system or exhaust components can trigger ignition. On an electric UAV, the beam cooking through the fuselage reaches the battery pack or motor controller, and that's the end of the flight. Either way, the drone doesn't explode dramatically at distance. It just stops flying and drops. Sometimes there's a small fire on the way down. Mostly it just falls. That last detail is something Iran's planners didn't fully account for, and it matters operationally. When a missile intercept happens, both sides know. There's a detonation, a debris field, a visible event that tells the attacking force its drone was stopped. The swarm operators can count intercepts, adjust, and keep pushing. With a laser kill, the feedback loop breaks down. A drone goes offline and the operators have no immediate way to know why. Signal failure, mechanical fault, or something they can't see burning through the airframe from 12 kilometers away. The swarm starts thinning, and the people who launched it don't have a clear picture of what's stopping it. U.S. Navy testing has demonstrated exactly this capability against drone targets under operational conditions, and the service has publicly confirmed Helios is deployed and functional. The Red Sea operations didn't just validate the threat picture, they put directed energy systems into a genuine combat environment for the first time, generating data on real-world performance that no test range can replicate. What Iran's operators would actually experience on the receiving end of a Helios engagement is a swarm that starts losing units with no obvious cause. No contrails, no explosion at range, no radio intercept of a missile launch command. Just drones going silent, one after another, while the ship they were sent to overwhelm keeps sailing. The swarm thins, the attack fails, and somewhere in an Iranian operations room, someone's trying to figure out what just happened to their strategy. What this means for Iran's strategy going forward. The math Iran built its doctrine on has flipped completely. A dollar defeating a $20,000 drone isn't a minor economic inconvenience. It's the entire logic of the swarm strategy running in reverse. Iran needed the cost exchange to work in its favor, and now it doesn't. So what does Iran do next? There are a few options on paper, and none of them are good. The first is speed. If a laser needs several seconds of dwell time to achieve a kill, then a faster drone reduces the window the beam has to work with. In theory, you could build drones that cross the engagement zone quickly enough to limit damage. In practice, faster drones cost more to produce, require better propulsion systems, and burn more fuel, which cuts range. The whole point of the Shahid approach was disposable cheapness. The moment you start engineering for laser resistance, you're spending more per unit, which means you need fewer of them, which means the swarm gets smaller, which means the saturation strategy stops working. Reflective coatings are the other idea that gets floated. Certain materials can deflect or disperse laser energy rather than absorbing it. So coat the drone's surface, and maybe you reduce the beam's effectiveness. The problem is that materials capable of reflecting the specific wavelengths, military lasers operate at add weight, add cost, and require manufacturing precision that a mass production drone facility isn't set up for. You've turned a cheap, expendable weapon into an expensive, specialized one. And you've still only bought a few extra seconds of dwell time, not immunity. The saturation angle is the only one with any real logic to it. If you can't make each drone harder to kill, send enough of them that the laser can't work through the whole swarm before some get through. To do that, you need to know the system's maximum engagement rate, how many drones per minute it can cycle through, and then exceed it by a wide enough margin that some survive. The engagement rate for Helios is not public information. Iran would be building toward a number it can't verify, spending money on drone production at a scale that starts to undermine the cost advantage that made the strategy viable in the first place. Every Iranian naval commander and IRGC planner operating in the Gulf now has to factor in that any U.S. Navy destroyer they're looking at might be carrying a weapon with an effectively unlimited magazine. That changes targeting calculus, risk tolerance, and the whole harassment playbook Iran has been running for years. There's an irony buried in all of this that's worth sitting with. Iran's persistent drone pressure in the Gulf and the Red Sea, the harassment, the Houthi campaigns, the cost exchange problem that had Western navies genuinely worried. That pressure is a big part of why the US moved so fast to get directed energy systems operational. Iran kept poking at the vulnerability, and the US responded by closing it. The aggression that was supposed to stress American naval capacity may have done more to accelerate American laser development than any Pentagon budget cycle would have on its own. Iran spent years building a strategy around a math problem it thought the US couldn't afford to fix. Then the US fixed it for roughly $1 a shot. Deep underground, behind dozens of meters of solid rock, Iranian scientists believed they'd found the perfect shield. The logic seemed sound. No air force in the world could reach them down there. But here's what they got wrong. The deeper you bury a nuclear program, the more precisely the US military has learned to target it. What we're going to show you is the weapon system built specifically to solve that problem, and why no bunker Iran can realistically build or operate will keep its program safe. The bunker strategy: why Iran went underground. Iran didn't decide to go underground on a whim. It watched what happened to Saddam Hussein's nuclear ambitions after the Israeli strike on Osirak in 1981. And it watched what happened to Libya's Gaddafi after he gave up his weapons program and was removed anyway. The lesson Iran took from both of those situations was simple. If you want a nuclear program to survive, you can't leave it sitting on the surface where anyone with a GPS coordinate and a large enough bomb can reach it. So Iran started digging. The most well-known result of that strategy is Fordow. It sits near the city of Qom, carved into the rock of a mountain rather than simply buried beneath flat ground. The Iranians chose that site deliberately. The mountain itself adds protection that poured concrete alone can't replicate. At reported depths of around 80 to 90 meters below the surface, the facility was designed from the start with one specific threat in mind: American and Israeli air power. The thinking behind it is straightforward physics. The deeper a structure sits, the more material a warhead has to pass through before it reaches anything worth destroying. At 80 meters of rock and reinforced concrete, you're outside the reach of almost every conventional airdrop weapon ever built. Iran's engineers knew the specifications of the munitions that existed when Fordow was being constructed, and they built accordingly. But depth wasn't the only layer of the strategy. Iran deliberately spread its nuclear work across multiple sites: Natanz for centrifuge operations, Iraq for a heavy water reactor, Isfahan for uranium conversion, and Fordow for the enrichment work considered most sensitive. The logic of dispersal is that any adversary planning a strike has to hit all of them simultaneously, or accept that whatever they don't hit will survive and continue operating. Miss one, and the program lives. There's also the political dimension to dispersal. Striking a single facility can be framed as a limited, targeted operation. Striking 6 or 8 sites scattered across a country the size of Iran starts to look like a war, and that calculus has historically made Western governments hesitant to act. For years, that combination, depth plus dispersal plus political complexity, gave Iran genuine protection. Defense analysts in Washington and Tel Aviv debated openly whether Fordow was simply out of reach. Some concluded it was. The Iranians were following that debate closely, and what they heard gave them confidence the strategy was working. What they didn't fully account for was that the US military was following the same debate, drawing the opposite conclusion, and quietly funding the answer. That answer didn't come from diplomacy. It came from a weapons program that had been running in the background for years, built around a single question. What does it take to reach a target that conventional munitions simply cannot touch? The weapons built to answer the bunker, the GBU-57 Massive Ordnance Penetrator, doesn't have a subtle name, and it wasn't designed for subtle work. It weighs 30,000 pounds. To put that in context, that's roughly the weight of 2 full-grown African elephants, packed into a single weapon and dropped from altitude at high speed. The US Air Force developed it for one purpose: reaching targets that nothing else in the arsenal could touch. The way it does it comes down to engineering that looks almost crude until you understand the physics. The outer casing is hardened steel, thick enough to survive the violent deceleration of punching through rock and reinforced concrete without the weapon breaking apart before it reaches its target depth. Inside, a delayed fuse gives the warhead time to travel down through the layers of material before it fires. The result is a weapon that can penetrate more than 60 meters of reinforced concrete and considerably more in softer ground before the 5,300-pound explosive fill detonates in whatever space it's reached. That number matters. 60 meters of reinforced concrete is a different problem than 60 meters of mountain rock, and the distinction is worth holding on to because it becomes important when we get to Fordow specifically. The only aircraft in the U.S. inventory capable of carrying the MOP is the B-2 Spirit, and it carries 2 of them. That's not a limitation of the aircraft so much as a reflection of how big the weapon actually is. The B-2's bomb bay was modified specifically to accommodate the MOP, meaning the Air Force committed real money and engineering time to making this delivery possible. You don't do that for a contingency plan. You do that because someone made a decision that this capability needed to exist and be ready. The MOP didn't appear from nowhere. It was preceded by the GBU-28, which became famous during the Gulf War in 1991. A 5,000-pound weapon that could punch through about 6 meters of concrete. At the time, that was enough to threaten the bunkers Saddam Hussein was using. But as Iran and North Korea watched that conflict and started building their own underground infrastructure, they built deeper. The GBU-28 stopped being a credible threat to the facilities they were constructing. The gap between what the U.S. could deliver and what adversaries were burying kept widening through the 1990s and into the 2000s. The MOP program was the direct institutional response to that gap. Congressional documents from the mid-2000s name Iran and North Korea explicitly as the threat scenarios driving the weapons development. The U.S. government wasn't being subtle about what this was for. The MOP reached operational status around 2011, and the Air Force has continued refining it since. At least 2 upgrade programs have improved its guidance systems and fusing to address specific feedback about penetration, performance against particular soil and rock compositions. That last detail is worth sitting with. The upgrades weren't generic improvements. They were responses to specific target characteristics, which means U.S. planners have been modeling Fordow and facilities like it in enough detail to identify exactly what adjustments the weapon needed to defeat them. The MOP wasn't just built to reach underground facilities in general. It was progressively refined to reach the specific ones that matter most. Penetration depth alone, though, is only part of the equation. Getting a 30,000-pound bomb to the right coordinate over defended territory without being shot down before it releases, that's a separate problem entirely, and it required a separate solution. Delivery, precision, and the platforms that make it work. The B-2 Spirit is the reason any of this works. Without a platform that can carry the MOP into defended airspace and release it accurately, the weapon is just an engineering achievement sitting in a hangar. Stealth is what converts that engineering into an actual military option. The B-2's radar cross-section is roughly the size of a large bird, a product of its flying wing shape, radar-absorbent surface materials, and the careful internal routing of engine exhaust to reduce heat signatures. Iranian air defenses are built around radar. They need to detect, track, and engage an incoming aircraft in a sequence that takes time. The B-2 breaks that sequence at the first step. If the radar can't produce a reliable track, the missiles that depend on that track can't fire effectively. The aircraft reaches its release point, drops its payload, and exits before the defense system has resolved what it was looking at. Precision is the other half of that equation. The MOP uses a combination of GPS guidance and an inertial navigation system that runs independently in case GPS signals are jammed or degraded. Together, they put the weapon within a few meters of its target coordinate. And that accuracy is what makes sequential strikes possible. You can drop the first weapon into a specific entry tunnel, then drop the second through the hole the first one created, driving the destruction progressively deeper into the structure. That's not a theoretical concept. It's a documented strike methodology the Air Force calls reattack. and it was specifically developed to address cases where a single pass isn't sufficient to guarantee destruction. But before any weapon leaves the aircraft, intelligence has to do its work. ISR, intelligence, surveillance, and reconnaissance, is what tells planners where exactly to aim. Satellites, signals collection, and aerial reconnaissance over years of observation have produced detailed models of facilities like Fordo, where the access tunnels enter the mountain, where the ventilation shafts run, where the power infrastructure connects, and where the internal chambers sit relative to the surface above them. Dropping a weapon accurately onto a coordinate is simple. Knowing which coordinate to give it, the one that collapses the right tunnel or severs the right shaft, is the product of years of collection work. The weapon and the intelligence system feeding it are inseparable. Now factor in the B-21 Raider, which has entered operational service and carries the same heavy payload capability as the B-2. The B-21 was designed with lessons from decades of stealth operations folded into its architecture from the start, rather than retrofitted over time. Its manufacturing approach also means the Air Force can build more of them at lower cost, which changes the calculus around how many aircraft are available for a given mission. The B-2 fleet is small, 20 aircraft total, and not all of them are mission ready at any given time. The B-21 is intended to grow that number considerably. More aircraft means more simultaneous strike packages, which matters directly for the dispersal problem Iran built its program around. The more sites you can hit at once, the less the dispersal strategy protects. Iran's engineers designed Fordo with the threat environment of the early 2000s in mind. The delivery systems flying today are a generation past what those engineers were modeling, and the generation coming next is further still. The physics problem Iran can't solve. Here's the constraint that no amount of concrete or political maneuvering can fix. The deeper you bury a facility, the harder it becomes to actually run one. Enrichment centrifuges are precision instruments. They spin at tens of thousands of rotations per minute and require stable power, stable temperature, and constant maintenance. The deeper underground you place them, the more complex and expensive the infrastructure keeping them alive becomes. Ventilation shafts to remove heat, power lines running down from the surface, supply tunnels wide enough to move equipment in and out. Every one of those systems is a structural dependency. Sever the ventilation and the facility overheats. Cut the power and the centrifuges stop. Collapse the access tunnel and no one gets in or out. The mountain protects the facility from above, but it also creates a set of choke points that a sequenced strike package is specifically designed to exploit. That's the part of bunker busting that rarely gets discussed. It isn't just about driving a warhead through the roof. A coordinated strike targets the tunnel entrances, the ventilation outlets, and the external power nodes in a sequence that leaves the interior intact but completely inoperable. A facility that survives a strike in that condition is still offline for months, possibly years, while the damage is assessed and the infrastructure rebuilt. From a military planning perspective, that outcome is nearly as good as destruction, because the time it buys is the point. Now apply that to Fordo specifically. The facility sits at a depth where the MOP's penetration capability against the rock composition of that mountain sits at the edge of what's publicly confirmed. And US officials have acknowledged that tension openly, then pointed to the upgrade programs that followed. What those upgrades addressed, based on what's been reported, was exactly that margin. The weapon was improved to close it. Iran's engineers face a dilemma with no clean exit. Push the facility deeper to stay ahead of penetration capability, and you make the operational problems worse. Longer ventilation shafts, longer supply lines, more surface infrastructure that satellites can image and strike packages can target. Stay at current depth and accept that the MOP, delivered accurately and sequentially, puts the facility at genuine risk. There's no depth that solves both problems at once, because the geological constraints that limit what a bomb can reach are the same constraints that limit what an engineering team can build and sustain. The bunker was always a bet that the weapons pointed at it would never quite catch up. That bet is no longer paying out. Where this leaves Iran, no underground facility survives indefinitely against an adversary with the will to use what it has built. That's not a political statement. It's the operational conclusion that falls out of the physics and the engineering on both sides. Iran's nuclear timeline has always been shaped by diplomacy, sanctions, and internal politics. What's changed is that the military dimension now adds a hard constraint that those other factors can't negotiate around. The US has the weapon, the platform, the intelligence picture, and a demonstrated willingness to act when it judges the moment right. Israel has struck Iranian assets before and has been explicit about what it will not accept. Both of those realities exist independent of whatever is happening at the negotiating table. The bunker gave Iran's program survivability it didn't have before. What it didn't give Iran was a permanent solution. It gave the program more time. And time, in this context, is running out faster than the mountain overhead would suggest. The bunker was Iran's answer to air power, and the MOP was America's answer to the bunker. That exchange is effectively over, and only one side came out ahead. A $35,000 drone has changed the course of modern warfare in ways few anticipated. Iran spent years developing a weapon that struck fear across the Middle East. Affordable, relentless, and deployed in overwhelming numbers. Then the United States executed an unprecedented strategy. It captured the very same drone, rebuilt it, stamped it, made in America, and turned it against its creators. How can a nation's own weapon be used against it? And what does this mean for the future of war? Join us as we reveal how the United States just cloned Iran's most feared drone and how it changes everything. For years, the United States military operated with one unspoken assumption, that raw technological superiority would always be enough. The idea that a drone costing roughly the same as a used car could challenge that dominance seemed almost laughable. America had stealth fighters that cost over $100 million each. It had cruise missiles that could thread a window from 1,000 miles away. It had aircraft carriers that projected power across entire oceans. The notion that a cheap, propeller-driven flying bomb could threaten any of that seemed almost absurd. Then came the Shahed. Iran's Shahed 136 is not an impressive machine on paper. It is a delta-winged, propeller-driven drone with a small warhead and no pilot. It does not evade radar with cutting-edge stealth coatings. It does not fire back when attacked. It flies relatively slowly, at low altitude, guided by GPS coordinates to a pre-programmed target. And when it arrives, it explodes. That is the entire concept. There is no recovery. There is no second mission. The drone is the weapon, and the weapon is expendable. And yet this relatively unsophisticated drone did something that billion-dollar weapon systems could not. It broke the economics of modern air defense. And once it broke them, nothing in the calculus of modern warfare was ever quite the same again. To understand why the Shahed was so strategically disruptive, you have to understand how air defense economics work. Every air defense system operates on a basic principle. The cost of intercepting an incoming threat must be justified by the value of what you are protecting. For most of military history, that equation made sense. Incoming missiles and aircraft were expensive to build and operate, so spending $1 million to shoot one down was rational. The attacker was losing something valuable every time they fired. The defender was spending money, but so was the attacker. The Shahed shattered that logic completely. When Russia began deploying Iranian-supplied Shahed drones against Ukraine in massive numbers, Western defense analysts watched in quiet horror. Not because the drones were destroying targets with pinpoint precision, but because of what it was costing to stop them. Ukraine and its allies were firing Patriot interceptors worth over $1 million each to destroy drones that cost somewhere between $20,000 and $50,000 to build. The attacker was spending a fraction of what the defender was spending. Every single engagement was a financial victory for Iran and Russia, regardless of whether the drone hit its target or not. The Shahed did not need to be accurate. It needed to be plentiful. And it was. Thousands of them were produced, deployed, and launched, attacking from multiple directions simultaneously. They flew at night to complicate visual detection. They flew low to complicate radar detection. They forced defenders to make impossible choices at every engagement. Exhaust your interceptor stockpile or let them through and accept the damage. Either way, the attacker benefits. This was the strategic lesson that shook every major military on Earth. The United States military studied this lesson very carefully. Defense analysts wrote about it. Think tanks published reports on it. The War Zone, one of the most respected military publications in the country, had been arguing for years that America needed to be building tens of thousands of Shahed clones immediately. The logic was simple and uncomfortable. If this strategy works against us and our allies, we need to be able to use it too. And we need to be able to use it at scale. And then America did exactly that. The low-cost, uncrewed combat attack system, known as Lucas, is the American answer to the Shahed 136. And the connection between the two is not subtle or theoretical. It is direct, deliberate, and openly acknowledged. American officials have described the process without apology. The United States captured one of Iran's Shahed drones, extracted its internal components, sent them back to engineers in the United States, rebuilt the system from the ground up using American manufacturing and American technology, added significant upgrades, and then deployed it against the very country that designed the original. CENTCOM Commander Admiral Brad Cooper put it in terms that left no room for interpretation. He told reporters that the United States captured the Iranian drone, pulled the guts out, sent it back to America, put a Made in America stamp on it, brought it back, and started shooting it at the Iranians. That is not a paraphrase. That is the admiral in charge of the entire Iran campaign, describing the program with remarkable candor at a press conference in Tampa, Florida. The drones are manufactured by SpectreWorks, a company based in Phoenix, Arizona. Each unit costs approximately $35,000. A Tomahawk cruise missile costs between $2 million and $2.5 million per shot. An air-launched cruise missile currently in service costs over $1 million. For the price of a single Tomahawk, the United States can now field over 50 Lucas drones. But Lucas is not simply a cheaper version of America's existing weapons. It represents a fundamentally different philosophy about what a weapon is supposed to be and how it is supposed to be used. Traditional American military doctrine has always been built around the principle of preservation. The entire procurement culture of the American military is built around the idea that each platform is a precious, irreplaceable asset. Lucas, however, inverts that logic entirely. These drones are designed from the start to be expended. They are not supposed to come back. The goal is to produce them so quickly and so cheaply that losing one in combat is strategically irrelevant. Defense planners call this concept attritable systems, platforms that are deliberately designed and accepted to be used up in combat. It is a radical departure from how the United States has approached weapons procurement for generations, and it reflects a hard-won recognition that in a conflict against an adversary willing to absorb enormous losses, the ability to match volume matters as much as the ability to field superior technology. The upgrades that America added on top of the Iranian original make Lucas significantly more capable than the weapon it was modeled after. The differences are not cosmetic, they are operationally transformative. Where the Shahed 136 flies a fixed GPS route to a pre-programmed coordinate and strikes whatever happens to be there when it arrives, Lucas operates in an entirely different tactical dimension. Multiple Lucas drones can communicate with each other while airborne. They can share sensor data, coordinate their approach vectors, and adjust their targeting based on what other units in the swarm are detecting in real time. This is autonomous cooperative behavior among multiple drones executing a shared mission. Some units in the fleet are equipped with Starlink satellite terminals, giving them beyond line-of-sight connectivity that allows targeting information to be updated while the drone is already in flight toward its objective. A Lucas drone can be launched, fly for hundreds of miles, receive updated coordinates mid-mission, and redirect itself to a new target without any human physically controlling it from moment to moment. The human remains in the loop in terms of authorizing the mission and approving the target list, but the execution is autonomous. The original Shahed was a blunt instrument designed for volume. The American version is a precision instrument that also happens to be available in volume. Lucas drones can be launched from multiple platforms, catapult systems on the ground, vehicle-mounted mobile launchers, and critically, from ships at sea. They were test launched from the Independence-class littoral combat ship USS Santa Barbara in the Persian Gulf before they ever saw combat. That naval launch capability is strategically significant. It means Lucas is not dependent on fixed airstrips that can be targeted and destroyed. It can be deployed from almost anywhere across a vast operating area, which makes the launch infrastructure itself extraordinarily difficult to suppress. CENTCOM established Task Force Scorpion Strike in December of 2025, following directives from War Secretary Pete Hegseth to accelerate the acquisition and deployment of cost-effective drone technology. It was the first squadron in American military history dedicated entirely to one-way attack drones. The mission was straightforward: provide affordable, rapidly deployable offensive drone capability to commanders in the Middle East as quickly as possible. The first combat use of Lucas came during Operation Epic Fury, the joint United States and Israeli military campaign targeting Iranian assets that began in early March of 2026. Task Force Scorpion Strike used Lucas drones in the opening salvos of the campaign. They were fired at unspecified Iranian targets on the first day and used repeatedly in the days that followed. For the first time in history, American forces were using mass-produced, low-cost kamikaze drones in sustained combat operations, the same category of weapon that had been exclusively associated with Iran and Russia just years before. When asked directly how effective Lucas had been in combat and how much it was helping preserve the stockpile of more expensive munitions, Admiral Cooper gave a two-word assessment: indispensable. That single word from the commander of United States Central Command is worth dwelling on, meaning the campaign as conducted could not have been executed in the same way without it. When asked what kinds of targets Lucas had been used against, Cooper's answer was equally economical: good ones. The strategic impact of Lucas extends well beyond any individual strike or any single campaign. For years, one of the most serious concerns animating American military planning around a potential conflict with Iran was the question of magazine depth. Iran possesses thousands of drones and missiles. Producing enough expensive cruise missiles and interceptors to match that volume was economically and industrially unsustainable over a prolonged conflict. The fear was that Iranian barrages would outlast American and Allied stockpiles, forcing a choice between accepting devastating strikes or escalating beyond what the political situation could bear. Lucas has directly addressed that fear. Iran's response to all of this was as revealing as it was predictable. Rather than acknowledging that the United States had studied their approach and built a superior version of their own weapon, Iranian military officials pivoted to accusation. The spokesperson for Iran's Khatam al-Anbiya central headquarters publicly charged that America and Israel had copied the Shahed design and were deploying Lucas drones specifically to frame Iran for drone attacks across the region that they themselves were carrying out. The allegation was elaborate. Lucas was not a weapon aimed at Iran, but an impersonation designed to make Tehran look responsible for strikes it had nothing to do with. Consider what that accusation actually reveals beneath the political theater. Iran built a drone so effective, so distinctive in its design, and so thoroughly associated with Iranian military operations across the Middle East that when America built a near-identical version, Iran's instinct was not to acknowledge the imitation. Their instinct was to claim that America was using the similarity to commit fraud. That response tells you everything about how central the Shahed had become to Iran's sense of its own military identity. And it tells you everything about how completely Lucas had disrupted that identity.
Germany is no stranger to producing top-of-the-line weapons and ammunition. Their commitment to innovation and engineering excellence has earned them a formidable reputation in the world of military technology. German tanks, in particular, are renowned for their balance of firepower, protection, and mobility. These tanks have been deployed in various conflicts, showcasing their mettle in Afghanistan, the Balkans, and even in peacekeeping exercises during the Cold War. They have proven their worth in real combat situations. Now that some of these German tanks have been sent to Ukraine, how does Russia react? Join us as we explore this deadly German supertank that shocked Russian invaders in Ukraine. Germany's decision to equip Ukraine with deadly supertanks represents a significant boost to Kyiv's defense capabilities in the ongoing conflict against Russian forces. The massive tank, the Leopard 2, is often considered one of the world's best main battle tanks. It hails from Germany, manufactured by the renowned company Krauss-Maffei-Wegmann GmbH. This tank, belonging to the third post-war generation, is operated by a crew of 4. What makes the Leopard 2 stand out are its remarkable features. These include a flawless fire control system, a formidable gun, and robust armor. Astonishingly, despite its considerable weight of around 70 tons, it can reach speeds of up to 72 kilometers per hour and come to a halt within seconds. Originally adopted by West Germany in 1979, the tank proved its worth and was subsequently exported to other nations. In fact, the Leopard 2 dominated the tank market in Europe, with only a few countries like England, Italy, and France opting for the development of their own main battle tanks. Its production began in 1979, and its initial buyer was Denmark, choosing the Leopard 2 over the American M1 Abrams due to cost considerations. Subsequently, Switzerland in 1983 followed suit, leading to other countries adopting this powerful machine. While the production of the Leopard 2 ended in 1990, this tank continues to receive various upgrades. The latest and most advanced version is the Leopard 2A7+, which many experts hail as the best main battle tank currently available. One of the most striking features of the Leopard 2A7+ is its firepower. This tank is armed with a 120mm smoothbore gun, which is a testament to its ability to engage and destroy a variety of targets, including heavily armored vehicles. The Leopard 2A7+ also boasts a fully automatic ammunition handling system, ensuring a rapid and continuous rate of fire. But that's not all. The tank is also designed for versatility. It can fire kinetic energy rounds, which are highly effective against heavily armored targets, as well as programmable airburst ammunition. This versatility means the Leopard 2A7+ can adapt to different combat scenarios, making it a formidable force on the battlefield. The protection offered by the Leopard 2A7+ is equally impressive. It features Chobham composite armor, known for its excellent protective properties. This tank also has additional armor modules to enhance its front protection, ensuring that it can withstand various threats. Its turret is protected by thick composite armor, providing a high level of crew safety. Mobility is another key aspect of this super tank. It's powered by a V12-cylinder 4-stroke liquid-cooled MTU 873K501 diesel engine with a power output of 1,500 horsepower. This powerful engine allows the tank to accelerate to speeds of up to 70 kilometers per hour, despite its weight of around 70 tons. It's a blend of power and agility that's essential for maneuvering on the battlefield. Additionally, the Leopard 2A7+ is equipped with advanced fire control systems. These systems provide the tank with excellent accuracy and targeting capabilities, allowing it to engage and eliminate threats effectively. Its laser rangefinder and thermal imager, integrated into the gunner's main sight, ensure precise target acquisition. It's an impressive fact that this tank can be configured for different roles, such as a main battle tank or an armored recovery vehicle, making it a versatile asset for any military. However, it's crucial to mention that Ukraine is expected to receive older Leopard 2A4 and possibly Leopard 2A5 tanks. These tanks boast the classic German layout with a rear-mounted engine, a self-supporting turret in the center of the hull, and control units in the front. They are equipped with Chobham combined armor and, in the case of the Leopard 2A5, additional armor modules on the frontal plate, significantly enhancing protection. The Leopard 2A4 was first introduced in the late 1980s. It is an earlier version of the Leopard 2 series and is known for its exceptional balance of speed, protection, firepower, and capacity. With a 120mm smoothbore gun, it's capable of firing a variety of rounds, making it a formidable opponent on the battlefield. The tank's armor, designed to withstand a variety of threats, provides solid protection to its crew. One unique aspect of this tank is its mobility. It's powered by a 1,500 horsepower engine, allowing it to reach speeds of up to 70 kilometers per hour. This blend of power and speed is crucial for maneuvering in combat situations. In fact, the Leopard 2A4 was often compared favorably to its contemporaries, including Soviet tanks like the T-72 and T-80. On the other hand, The Leopard 2A5 represents an evolution of the Leopard 2 series. Introduced in the early 1990s, it brought several improvements to an already impressive platform. The most noticeable upgrade is its advanced armor protection. The Leopard 2A5 features additional armor modules on the front, increasing its protective capabilities even further. This tank's gunnery systems have also been enhanced. It maintains the 120mm smoothbore gun, but with improved stabilization. Its fire control systems are top-notch, offering precise targeting capabilities. The Leopard 2A5's combat effectiveness has been taken up a notch with the addition of a thermal imager, allowing it to operate effectively day and night. Both the Leopard 2A4 and 2A5 have made their mark in history, demonstrating excellence in armored warfare. These tanks have seen action in various conflicts, proving their worth on the battlefield. They remain iconic symbols of the dedication to innovation and defense in the world of military technology. However, one of the drawbacks of the Leopard 2 series has been its relatively weak underbody protection, which ranges from 20 to 60 millimeters. In the event of a mine explosion, the driver's survival was highly uncertain. To address this, the Leopard 2A4M and Leopard 2A6M introduced a superimposed armor plate under the tank, offering greater protection. However, whether these upgraded versions will be supplied to the Ukrainian army remains unknown. The Leopard 2's turret is another area of impressive protection. It features 860mm thick composite armor on the right side and 660mm on the left, primarily due to the commander's EMES-15 observation unit located on the right. Additionally, the turret's side plates, angled at 30 degrees, are 310mm thick. Unlike Soviet tanks, where all ammunition is stored under the crew compartment, the Leopard 2 wisely separates the ammunition storage from the crew. There are 27 rounds of the first-round ammunition, and an additional compartment holds 15 rounds. This design is crucial in the event of an ammunition detonation, as the blast's energy can escape through specially designed windows, increasing the crew's chances of survival. Comparing this design to Soviet tanks, where ammunition storage below the crew compartment poses significant risks in case of an explosion, underscores the Leopard 2's safety measures. The significance of Ukraine receiving Leopard 2 tanks lies not only in their exceptional technical attributes, but also in the shift from using Soviet-made tanks to NATO standard equipment. This transition could potentially bolster Ukraine's capabilities in the ongoing conflict, as it continues to fight for its sovereignty. However, the exact impact of these NATO tanks on the course of the war remains to be seen. The Leopard 2 tank is a formidable piece of machinery, equipped with a V12-cylinder 4-stroke liquid-cooled MTU-MB 873 K501 diesel engine. It packs a punch with 1,100 kilowatts or 1,500 horsepower under the hood, enabling it to zip down the highway at speeds of up to 72 kilometers per hour. What's interesting about its drive system is that it's ingeniously designed as a one-piece engine block, allowing for a relatively swift replacement of the transmission set using a recovery vehicle, typically within a time frame of about 4 hours as stipulated by technical regulations. Now, when it comes to firepower, the Leopard 2 doesn't disappoint. Its primary armament is the fearsome 120mm smooth-bore gun, the Rheinmetall version L44. This potent gun, which remained standard up to the A5 version, boasts two-plane stabilization, enabling precise targeting and the ability to fire various types of shells, including the German DM-33 Bops with tracer. This formidable shell can pierce a substantial 560 millimeters of steel armor from a distance of 2,000 meters. It's a testament to the Leopard 2's firepower. The Leopard 2 is not all about its main gun, though. It comes with secondary armaments, including 2 machine guns, one of which is coaxially mounted with the main gun, and the other serves as an anti-aircraft gun. Different variants of the Leopard 2, be it German, Danish, or Swiss models, come equipped with various machine guns like the 7.62mm MG3, the 7.62 FN Mag, or the 7.5mm MG87, depending on the nation of origin. Remarkably, The Leopard 2 stores a substantial 4,750 rounds of machine gun ammunition. In terms of targeting and precision, the Leopard 2 is equipped with a top-notch fire control system known as the MS-15, featuring independent stabilization in 2 planes. The gunner's main sight is integrated with a Zeiss laser rangefinder and thermal imager. Furthermore, the gunner enjoys an 8-fold auxiliary periscope, the Faro Z18, enhancing target visibility. Meanwhile, the commander has an independent Rheinmetall Zeiss Peri R 17A2 periscope, which provides exceptional day and night visibility of targets up to a range of 3,600 meters. The fire control system is a crucial element, providing 3 range readings to the target within 4 seconds. This data is transmitted to the fire control computer, aiding decision-making. A notable feature is that the gunner can directly see the results of these calculations in digital form. The rangefinder boasts a remarkable maximum range of 10,000 meters with an accuracy of 20 meters per 10 kilometers, which allows the Leopard 2 to effectively target and eliminate moving threats, even while traversing rough terrain. In a nutshell, the Leopard 2's technical specifications, particularly the A4 and A5 versions, are certainly on par with the most advanced Soviet T-72 and T-80 tanks. However, it's essential to mention that these NATO tanks might face stiff competition from the Russian T-90 tank, which Russia has been supplying in large numbers to conflict zones. Now, let's pivot to the heart of the matter. How could these German Leopard 2 tanks potentially influence the Ukrainian-Russian conflict? The supply of 14 tanks from Poland, though significant, might not tip the scales dramatically in a war of this magnitude. However, the implications go beyond mere numbers. For a considerable time, NATO countries were hesitant to provide tanks to Ukraine. Concerns about maintenance and repair, given that all Western equipment supplied to Ukraine is repaired in the West, have been a roadblock. Moreover, there were concerns that inexperienced Ukrainian tank crews might not fully exploit the capabilities of NATO tanks, which could potentially harm the reputation of these formidable machines. Yet, the decision to supply tanks signifies NATO's confidence in resolving these challenges and its willingness to accept potential image losses. This initial delivery of 14 tanks could potentially set a precedent for more significant support in the future. Ukraine's Minister of Foreign Affairs, Dmytro Kuleba, has stated that 5 countries are ready to transfer their Leopard 2 tanks to Ukraine. These nations include Poland, Finland, Germany, Sweden, and Spain, boasting a collective arsenal of 1,233 Leopard 2 tanks across various modifications and technical conditions. This extensive support includes 389 Leopard 2A4 versions. Furthermore, reports suggest that British Prime Minister Rishi Sunak is contemplating the delivery of a tank company of 12 Challenger 2 tanks to Ukraine. The cumulative force of these armored units represents a substantial combat capability. With such a formidable armored force at their disposal, Ukrainian troops could potentially mount a significant offensive. For instance, they might consider launching an attack on Melitopol and Berdyansk, effectively severing the Russian land corridor to Crimea. Such an offensive could be a game-changer in this ongoing conflict, inspiring Ukrainians and their Western allies and potentially leading to even more substantial arms shipments. It could set in motion a transformative and far-reaching effect. Because the Leopard 2A, 4, and A5 are just enough to help bolster Ukraine's military power, there may be no need to send the latest edition of the Leopard 2 supertank to the country. Interestingly, Germany is even working on a replacement for these impressive tanks. The Kf-51 Panther represents a quantum leap in the world of main battle tanks, or MBTs. It was created from the ground up, integrating some of the most advanced technologies available, and it sets new benchmarks across various dimensions: lethality, protection, networking, reconnaissance, and mobility. Germany will be replacing its Leopard 2S with this tank. When we talk about the Panther's lethality, we're talking about a game-changer. It's armed with the Rheinmetall Future Gun System, or FGS, coupled with optimized sensor-to-shooter links, which gives it a lethal edge. The FGS is the star of the show, featuring a 130 mm smoothbore gun and a fully automatic ammunition handling system. This combination packs a punch, offering superior firepower against all current and foreseeable mechanized targets. Notably, the autoloader can maintain a substantial 20 ready rounds, which makes the FGS more than 50% effective for engagements at much longer ranges compared to the current 120 mm systems. To add to the Panther's versatility, the FGS can fire kinetic energy rounds, programmable airburst ammunition, and the necessary practice rounds. But that's not all. The Panther also comes equipped with various armament options, ensuring it can deliver concentrated firepower for long-range strikes and against multiple targets. This arsenal includes a 12.7 mm coaxial machine gun and the Hero 120 loitering munition. The coaxial machine gun is designed to supplement the main weapon and offers a range of integration options for remotely controlled weapon stations, or RCWS. These systems enhance proximity and drone defense flexibility. Additionally, the Panther on display at Eurosatory 2022 boasts Rheinmetall's new Natter, or Adder RCWS, in a 7.62 variant. Moreover, Rheinmetall's partner, U-Vision, contributes the Hero 120 loitering munition, which can be integrated with the launcher, boosting the Panther's ability to strike targets beyond its direct line of sight. Interestingly, the KF-51 Panther is the first MBT to introduce an integrated survivability concept that's truly outstanding. This concept blends on- and off-platform sensors with active, reactive, and passive protection, not to mention a dedicated Top Attack Protection System, or TAPS. What does this mean? It means the Panther is actively shielded against a wide array of threats, particularly kinetic energy threats, all without increasing the tank's weight. TAPS works to deflect threats from above, while the rosy smoke obscurant system served to cloak the Panther from prying enemy eyes. To further enhance its survivability, the tank is equipped with a digital NATO Generic Vehicle Architecture, or NGVA, enabling it to deploy additional sensors for detecting launch signatures. This capability is complemented by the tank's ability to recognize and neutralize threats at an early stage, thanks to its pre-shot detection capability. What's more, the Panther is also cyber-hardened and designed to operate effectively in contested electromagnetic environments. When it comes to controllability and networking, the Panther offers a fresh operating concept. It's primarily designed for a 3-person crew, consisting of the commander, gunner, and driver in the turret. But there's an additional operator station, which can accommodate a weapons and subsystems specialist or command personnel, such as the company commander or battalion commander. This versatility allows the Panther to adapt to a variety of operational scenarios. So, while Leopard 2 is very good and will be serving Ukraine in the war, Germany is moving on to another formidable MBT. However, in addition to the tanks to be delivered to Ukraine, Germany will also be sending the country some Marder infantry vehicles. The specific number of Marder vehicles that Germany will provide has not been officially disclosed, but German government spokesperson Steven Hebestreit indicated that approximately 40 Marders would be supplied, enough to complete a battalion. The Marder infantry fighting vehicle, a 30-ton tracked vehicle equipped with steel armor, will be another significant upgrade for the Ukrainian Army's mechanized infantry. Paired with the M2 Bradley IFVs from the United States, these vehicles offer Ukraine the mobility, protection, and firepower necessary to launch a major offensive. The origins of the Marder can be traced back to World War II, when the German army realized the importance of having infantry support to secure conquered territory. The Marder infantry fighting vehicle entered service in 1971 and has undergone continuous upgrades since. Despite its age, the Marder remains a top choice for its balance of speed, protection, firepower, and capacity. It has proved its effectiveness in various battles, including deployments in Afghanistan and the Balkans. The Marder is powered by a 600-horsepower, 6-cylinder liquid-cooled diesel engine, providing excellent mobility. Its suspension system, hydraulic shock absorbers, and advanced transmission make it a reliable and agile vehicle. It can reach a maximum road speed of 40 miles per hour, matching the speed of the German Army's Leopard tanks, and has a maximum cruising range of 310 miles. This vehicle can even navigate through deep water, fording to a depth of up to 8 feet with a kit. It can tackle steep gradients, side slopes, vertical obstacles, and trenches. making it a versatile and adaptable vehicle for various terrains. In terms of firepower, the Marder is armed with a primary 20mm Rheinmetall Mk 20H202 automatic cannon, capable of firing 1,000 rounds per minute, with a range of 2,734 yards for land targets and 1,600 yards for air targets. This cannon's accuracy and rapid fire rate make it a formidable weapon. Additionally, the Marder features a 7.62mm coaxial machine gun and 2 banks of 76mm smoke grenade dischargers. While the incoming U.S. Bradley vehicles are equipped with TOW missiles, the Marder's primary armament and secondary machine guns make it a versatile asset for both combat support and infantry transportation. Germany's decision to supply Marder infantry fighting vehicles and Leopard 2S to Ukraine, along with support from other nations, showcases the international commitment to bolstering Ukraine's defense capabilities. It's a move in the right direction. Thanks for watching. While you're still here, click on the link appearing on your screen to watch another of our interesting videos. See you there.